Hello and welcome back to the Science of Concrete Materials class. This is lecture number 39 of the class, and we will continue our discussion on the durability module of the class. Last lecture we stopped here at the subject of sulfate attack. We're still on the chemical types. We stopped here at the sulfate attack. Perhaps the most widespread and common form of chemical attack is the action of sulfates on concrete. Sulfates are often present in groundwaters, particularly when high proportions of clay are present in the soil, and also in seawater, which has sulfates as major constituent. Groundwaters may have local concentration of sulfate in the vicinity of industrial waste, such as mine tailings, slag heaps, and rubble fills, and stuff like that. Okay. Sulfates, could also be present in rainwater from air pollution or produced by biological growths. This also may cause slow deterioration even in concrete above ground. Okay, but although very rare, but it's the potential is there. Okay, so, and also I'd like to mention, because sulfate attack broadly divided into two types: the external sulfate attack, where the source of sulfate will be external to the concrete, as the sources I just described. We also have another type referred to as internal sulfate attack or delayed Ettringite formation. I will just briefly mention this type, and the focus of the discussion will be on the external sulfate attack type. Okay. Okay, so the damage caused by the sulfate attack may involve, cracking and expansion of concrete as a whole, as well as the softening and disintegration of the cement paste in certain types of the attacks, as we will see. So let's look at the mechanism of the sulfate attack. Sulfate attack is actually, rather a complex process that may involve all of the hydration products produced by the Portland cement. It depends on the sulfate ions concentration. The solubility in gypsum in water at normal temperature is rather limited, approximately 1400 milligram per liter, measured as SO4. A higher concentration of sulfates in groundwaters are generally due to the presence of magnesium, sodium, or potassium sulfates. Okay. The form of sulfate ions, the cations present in the source of the sulfate attack, such as, for example, magnesium sulfate, take on a form different from that of sodium, as we will see. Also, the severity or the extent of the sulfate attack will be influenced by the cement composition, especially the C3A content, as we have discussed previously, if you recall. Okay, so if you remember, we talked about the certain forms in one way or in a different context, the forms of the sulfate attacks previously. So let's talk about them here in a different way. The chemical reactions in sulfate attack, there are several types. The first one, due to the formation of ettringite. So ettringite, we said it forms typically during the early reaction of the cement, and the ettringite that forms at as the addition of water, if you remember, we refer to as primary ettringite, and according to this equation right here. This typically forms, while the concrete is still in the plastic stage and really does not result in any damage. After this, when all the sulfates are consumed from the system before C3A, ettringite is converted to the monosulfoaluminate phase, which is this one, the lower sulfate bearing phase. Okay. Subsequently, due to the presence of calcium hydroxide in the hydrated cement paste, when a cement paste comes in contact with sulfate ions, typically from an external source, the monosulfate is converted to the high sulfate form, which is the ettringite, according to this equation. Okay? So this is the reformation of ettringite. The formation of ettringite leads to expansion, or it is believed to do so. There is a general agreement that the sulfate-related expansion in concrete are associated with ettringite. However, the mechanisms by which the ettringite causes expansion is still a controversial subject, and really, it's the subject of an ongoing debate. The exertion of pressure by growing ettringite crystals, and maybe the swelling due to the absorption of water in alkaline environment, by poorly crystalline ettringite. The ettringite that forms in an alkaline environment usually poorly crystalline. So the absorption and the swelling due to the absorption of water and the swelling. These are the two accepted, or two of the several hypotheses out there, and they are basically supported by most researchers. Okay, so we have another mechanism for sulfate attack, which is due to the formation of gypsum. So gypsum formation as a result of the cation exchange reactions is also capable of causing expansion. However, it has been observed that deterioration of hardened Portland cement paste by gypsum formation goes through a process that first, leads to reduction of the pH of the system and loss in the stiffness and the strength, which, followed by expansion and cracking, and eventually transformation of the concrete into a mushy, non-cohesive mass. So depending on the cation type associated with the sulfate solution, for example, sodium, potassium, or magnesium, both calcium hydroxide and the calcium silicate hydrate present in the hydrated Portland cement paste may be converted to gypsum by the sulfate attack, as you will see here. Okay, the first type is the sodium sulfate attack, according to this equation. Okay, if the present form of the sulfate is the sodium sulfate, will react with calcium hydroxide in the presence of water, and we will have the result of that will be gypsum and sodium hydroxide. The formation of the sodium hydroxide as a byproduct of this reaction ensures the high alkalinity in the system, which is essential for the stability of the cementitious material, the calcium silicate hydrate. Okay, the case is different when the form of the sulfate presence in the form of magnesium sulfate, as you can see from these two equations right here. So, okay, the formation of the relatively insoluble magnesium hydroxide, okay, means the absence of hydroxyl ions in the solution. This means the calcium silicate hydrate is no longer stable and is also attacked by the sulfate solution. according to this equation, as you can see. So the magnesium sulfate attack is therefore more severe on concrete than in the case of sodium. So it makes a huge difference whether the sulfate are present in the form of sodium sulfate, for example, or in the form of magnesium sulfate, okay? Okay, so let's look at really the factors that influences the sulfate attack. Of course, as one would expect, the quality of concrete. The low permeability is key, and the low permeability is achieved by low water cement ratio, as we have been talking about all along throughout the class. The use of the SCMs, the supplementary cementitious materials, and we said this will play a double role here. The use of the SCMs remove the calcium hydroxide and, make less available for the formation of ettringite or gypsum, and also make the cement paste matrix denser and less permeable, okay? Also, low permeability is impacted, as we have seen, by adequate compaction and consolidation and by moist curing. Also, the sulfate attack, as you would expect, because aluminate are required for the formation of ettringite. So the cement type, the cement composition, especially C3A content, is very important. Also, the sulfate ion concentration. I will just have a few words to say here. I may have mentioned in a previous lecture about that, the ACI 318 code specify, severity of sulfate attack based on the concentration of the sulfate ions. Okay, so it classified them into, I think, four categories. The first one, we will consider that, the sulfate attack is negligible when the sulfate content is under 0.1% in soil, or under 150 parts per million in water. Okay, there shall be no restriction on the cement type and the water cement ratio. Okay, the second classification is the moderate attack. Okay, when the sulfate content is between 0.1 to 0.2% in soil, roughly 150 to 1500 part per million in water, the ASTM type 2 Portland cement or Portland pozzolan or Portland slag cement shall be used in this case with water cement ratio, less than 0.5, okay, for normal weight concrete. The third classification is the severe attack, when the sulfate content is between 0.2 to 2% in soil, or 1500 to 10,000 part per million in water. Then ASTM type 5 Portland cement with less than a 0.45 water cement ratio shall be used. Okay, we have the last classification, which is the very severe attack, when the sulfate content is over 2% in soil or over 10,000 part per million in water. Then ASTM type 5 cement plus a pozzolanic admixture shall be used, and water cement ratio shall be less than 0.45. Okay, so these the precautions that need to be taken to really mitigate or counter or combat the sulfate concentration in the soil or in the water, the groundwater. Okay. Okay, so if we to look more at the really factors that really influence or impact the sulfate attack. This, this is a holistic model right here. which shows the contributing or the factors that contribute to the occurrence of the external sulfate attack and how to prevent it. So the presence of water and the sulfate source right here. Of course, we need, in order for the sulfate attack to really occur, we have to have water, sulfate form, from an external environment in some form, and there has to be the concrete has to be permeable to basically allow for the transport of these ions into the concrete. Okay, so as you can see here, the presence of water and the source of sulfate in groundwater cannot be eliminated, because sometimes we cannot really choose where the structure will be built. So water is always there, and the sulfate in some form, in the external, in the soil will or the seawater will exist. Okay, so what is under our control is the concrete quality. So we can prevent the external sulfate attack by ensuring, that concrete we produce of a high quality. Okay, that means, as I mentioned in the previous slide right here, concrete has to be of low permeability, meaning we use some type of pozzolan, supplementary cementitious materials. We make sure adequate compaction, moisture curing, whatever we can to improve the quality of the concrete and prevent the formation of the compounds that will cause the damage. Okay. The other form of Ettringite formation is the Delayed Ettringite Formation. I said I'm going to mention this briefly because really it's a far more complex. It's a far more complex subject than what are the few points I'm going to mention here. I'm just mentioning these highlights here just for completeness so that you know about the subject. But the subject is far more complex than to present in a lecture or two. Okay, so how it happens, curing at elevated temperatures used in many precast plants, between 70 to maybe 88 degrees Celsius, between 158 and 190 Fahrenheit, can have negative implications involving sulfates. The high curing temperatures destroy primary ettringite, okay, and as a result, the sulfates as well as the alumina resulting from the decomposition of that ettringite appear to be absorbed by the calcium silicate hydrate. Okay, after cooling, however, the sulfate is again available to form ettringite, which is have been attributed, or some expansion or increase in volume has been attributed to such phenomena. Okay, so this form of sulfate attack, known as the Delayed Ettringite Formation, or short for DEF, okay, is distinctly different from that described earlier. Okay, the DEF is usually limited to cases where the cement has an SO3 to alumina ratio above 0.5. And again, this is not 100% set in stone, okay? But this what is reported in the literature. That's what I'm just reporting. Other than that, the subject is more complex and is impacted by many factors. And the concrete, exposed to significant moisture, the specific, mechanism of the DEF is not fully understood. But again, as reported in the literature, it does appear that, incipient damage from other causes such as alkali silica reaction or thermal gradients is a necessary component for the delayed Ettringite formation to cause any deleterious expansions. Okay, so the likelihood of DEF can be reduced by controlling the cement composition, maybe also using pozzolans and entrained air, okay, and limiting both the maximum curing temperature to maybe 70 degrees Celsius, and to the extent possible exposure to moisture, which is of course not the case except an internal concrete element like columns and walls may be not subject to rain or another source of water. And again, what I mentioned here is very brief and it does not even begin to address the subject. And as I said, I mentioned these points here just to make sure you are aware of the subject or know of it, but it's far more complicated, okay? So, okay, speaking of the sulfate attack, let's talk about, although I talked about this before, I just mention it here because we are on the subject of the sulfate attack, about the tests, what tests are done to predict sulfate attack. 2 ASTM tests provide basically a measure of the sulfate resistance of concrete. Neither, however, provides rapid results, and many different approaches have been used. We have the ASTM C452, which is, proposed for research purposes only, okay? Uses basically an abnormally high gypsum content in cement to test the sulfate resistance. It is a test, for the cement only and not for concrete. So this procedure, has several drawbacks. The major objection being that the test is too slow for use as, a routine specification test. So that the behavior of concrete does not necessarily parallel the behavior of the mortar bars done in the lab. Okay, and and that also realistic exposure conditions are not reproduced. Okay. Again, the test is only for use with Portland cement and does not assess the behavior of the blended cements, okay, or cements blended with pozzolans or slags. We also have the ASTM C1012, which is designed to provide a means of evaluating the expected sulfate resistance of concretes and mortars made using Portland cements, also blends of Portland cements and pozzolans or slags, or blended hydraulic cements in general. In this case, a mortar bar is exposed to a solution of sodium sulfate, or a mixture of sodium sulfate and magnesium sulfate, dependent on the outcome. The expansion is measured over time, and the value at 6 months is used as an acceptance criterion for sulfate resistance, for blended cements, which is classified as ASTM C595. But, again, clearly significant work is needed to produce really rapid test results for sulfate resistance. And that subject, is really open for new innovations if anybody is interested. Okay. So I'm going to stop here for now for this lecture, and I will continue again next time with the remaining chemical attack types, the alkali silica reaction maybe, and the corrosion. So until then, thank you for watching, and I will see you next time.